So why do we care about the ozone layer? Well, let's look at the biological response to radiation. Let's start with the nature of light. I'm pretty sure you've seen all this before, but it's not something you deal with every day, so let's go for a little review here. But light is in the form of waves, and we usually use the word light in terms of that small area of visible light, but this is called the electromagnetic radiation. And it is made up of waves. That little symbol here is called a lambda, and it is measured from the same point on two adjacent waves. And that's called a cycle. Usually it's peak to peak or trough to trough, or a point here to a point there. It doesn't really matter as long as it's uniform. But I want you to appreciate that the wavelength is inversely proportional to the energy. So longer wavelength means lower energy. Right? Longer wavelength equals lower energy. Okay. Over here we've got a higher energy wave, and you'll notice that she's got shorter wavelengths. She has a shorter distance between peak to peak. The other way we talk about the energy or behavior of a certain wave is to talk about its frequency. And it has a symbol either of small f in physics, or this is a nu, like a Greek n. I'm not even sure if it's a Greek n, but it's like a V with a little, one side's flat and the other one comes up. Unfortunately, it looks like V for velocity, so people get confused. But she's a frequency. That's the number of times the wave passes a fixed point in 1 second. Remember that for light is going to travel always at the same speed. Microwaves, UV, gamma, visible, they all travel at the speed of light. And this is called C, and she's equal to 3, and I can use an awful lot of significant figures here, but I'll just go to the 100th place, times 10 to the 8th meters per second. Fastest thing we know of. I think every couple of years somebody comes and says, "Oh, we've discovered something that goes faster than the speed of light," and then they are discredited. Well, I don't know. Well, someday, who knows what's going to happen? But this is the fastest speed of any known wave. All right. So the units of frequency are, you might have heard the hertz, like megahertz or kilohertz on the radio, and that simply means 1/2 So if you're standing right here, like here. Yeah, you're watching it, and this guy's moving at 3 times 10 to the 8th meters per second. You're counting how many times this guy hits you. Bang, 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 and that's your frequency. It's like waves of the water coming at you sitting in a stationary boat. And wavelengths, well, they've got nanometers here, the N for nanometers, but it's just a distance. It's a length. Okay. All right, so here's our electromagnetic spectrum. And this is pretty much where we live, the visible range. We'll move into the IR, the infrared, at points. You know, we all use the microwave oven, and we enjoy the radio waves coming and being collected by antenna. Over here, at higher energy, we have some dangerous stuff. We have gamma rays, X-rays, and UV. Down here is lower energy. And watch how it correlates to the wavelength. The longer the wavelength, the lower the energy. You're getting hit by radio waves right now, and you don't feel anything. They have very low energy. But if we look at various types of radiation, they seem different to our senses, but they really only differ in their respective wavelength and velocity. And you can see that the visible portion that we can see with our naked eye is a very small region. Its wavelength is at 400 to 700 nanometers. Longer than that, we call past the red is the longest, and past that is the infrared, right? And on the other end, we've got, if you remember the one Roy G. Biv, that was a way to remember the spectrum, which came first. So we've got red, orange, yellow, green, blue, indigo, and my friend violet right here. That's the other end. That's highest energy of the visible. And so what do we call the one past that? Why we call it ultraviolet, of course. Okay. Alrighty. So there she is, Roy G. Biv. And infrared, IR, the longest of the visible spectrum. And because we can see over here, we can kind of see things glowing with heat. The heat rays absorption causes molecules to do something different. Let's look to see what it does to matter. Well, infrared makes matter bend and stretch. Okay. Microwaves, they cause molecules to rotate. And in fact, this is what the early microwave ovens used to do. They were tuned to the rotational frequency of water. Most food has got plenty of water in it, so microwaves, the waves were low energy, but they were able to make the water molecules rotate, and then the friction of these guys rotating conductively heated the proteins and fats and sugars around them to heat up the entire piece of food. It's also why things that had no water in them, like China, did not warm up at the same point. They will warm up, though, conductively. It's like insulation. So if the heat radiates out from the water molecules to the plate, it probably gets warm underneath the plate. Maybe the whole plate gets warm after a while. All right, short wavelength range. This is high energy. And now we're getting closer to our friend. What does the ozone layer do? It includes ultraviolet, X-rays, and gamma rays, and these are dangerous to living matter. It can affect your DNA. What it does is, let's look at the different parts. It will cause breakage. It breaks bonds. It disrupts cells. It causes decidedly aggressive damage to us. Here we have infrared, IR, or heat radiation, and then we have our little microwaves, and that's molecules rotating. That's kind of what they look like. See, we keep talking about these chemical bonds, and I've tried to say to you that they're not really static, and here they make a huge point of that by making them look like springs. And yes, they can vibrate. Look at the arrows, and the whole guy can rotate and move around. Okay, the sun's radiation spectrum. Well, lucky for us, by far the most of the energy coming off of the waves of the sun, the electromagnetic waves of the sun, is in infrared. So about 50%, let's say about 50% is IR, and then about 40% is visible. And then the damaging is much smaller. And in fact, our atmosphere protects us from the high radiation, or we wouldn't be here. It's that damaging. Like I say, this high energy radiation would sterilize the whole Earth's surface. Okay. All right, so the biological effects depends upon, the energy that they have, the length of time you're exposed, and the sensitivity to that organism. So we have soybeans that are sensitive to UV radiation because they're a sensitive crop, and we also have phytoplankton in the oceans, which is sensitive. You think that that seems not very important, except they are a very big link in the food chain of the oceans. For us, the most deadly form of skin cancer, melanoma, is linked to the intensity of UV radiation and the latitude at which you live. So, what can it do to you? Oh, do you remember this poor woman they went after? There were like 10,000 sightings, or yes, searches for her on the internet. This was a tan woman, and she looks like she has been, tanned like in leather. But when you why use a sunscreen? Because you do have unexposed sun can cause wrinkling and sunburns, and probably more importantly, skin cancer. The rates of skin cancer are rising fast. We have now 50% greater chance of, the chances of getting melanoma, that most fatal of the skin cancers, has doubled since the 1990s. And this is all U.S. 50% of all cancer cases, over 1 million cases each year in the U.S., one person dies every year. And the reason is the decrease in the ozone protection. This is the stratospheric ozone, but also we spend more time in the sun as recreation and these wonderful tanning beds. 150 years ago, for Caucasians, it was a sign of great wealth not to be very white, and now they want to be tanned. I guess it shows leisure, or I do not know. Okay, so let's look at the number of people getting sun risk of skin cancer, and you can see that people without the protecting layers of melanin are going up very high. Okay. This melanin, which is Greek for black, provides protection by preferably absorbing harmful radiation. And notice this now, 2/3 of all white Australians now develop skin cancer. There are 3 different basic categories of UV radiation that depend upon energy. So the UVA is the least energetic, then you got UVB, and the most energetic is UVC. And it's not really a problem because most of it, it's totally absorbed by ozone and oxygen. When you see oxygen, they mean O2, and of course the ozone is O3. And in fact, the ozone absorbed about half of the UVB, and so we're getting, I don't think it's the least damaging, but it reaches the Earth in the greatest amount, that UVA stuff. Sun damage, the UVC is currently blocked by the ozone layer. The high radiation UVB does the most immediate damage. Sunburn, that's where we get most of the sunburn. But the lower radiation, now this is counterintuitive. She penetrates deeper into your skin, even though she's lower energy. Why is that? Well, it's because of the melanin. And this stuff absorbs the UV, the more energetic light, and it does protect the layers beneath, but it also is what gives, it causes it gets darker as it absorbs this light, so that's where the tanning comes in, the brown color in one's skin. And it stops it, though, from going in deeper into the sublayers of skin. Well, it doesn't stop UVA, and the UVA then happily moves into your deeper layers, and that's where we can get into the cancer, the skin cancer. So many sunscreens. What do they actually do? Most of them say UVA protection. UVB protection. That is to stop the sunburns. And a lot of them now say UVA, although there is no category or protection factor given for UVA. The SPF rating. They were good UV blocker. They've got some wonderful characteristics, like, for example, this one turns blue when you get too much UV light. So you start turning blue, and then you start looking at these higher and higher numbers, the sunscreen protection factor, and it measures only your UV protection only. You look for a label that says it protects you from UVA. I think most of them do now. And yeah, here we go. UVA, UVB. That's the stuff that keeps you from getting the skin cancer. Is it overkill when they say all these wonderful get SPF 100 plus? Look at the difference. It's 100 to 50 is marginal. If you look at the old standby 30, that deflects about 97%. And if you look at SPF 100, he does 99%, but it's a minimal or marginal increase. And the problem is that it lures you into a false sense of security. You think, oh, I can just put it on and I'm covered all day. But they rub off just as well as the SP30, and you should put it on every 2 hours. And you should put on a huge amount, a full shot glass. I know this SPF 100 is more expensive, so you're more likely to reapply a lot if it's the more standard SPF 30. Now, both these guys can lead to skin cancer, but the UVA is the bigger player in all this. Oh, and here's some lovely pictures of skin cancer just for your morning breakfast. Okay, you are trying to avoid long exposure just because you won't see any immediate effects. So you don't say, oh, I hurt, I'm leaving. You stay in the sun, and there's no official rating for UVB protection. I'm sorry, UVA protection like there is for UVB. So UVB, they have this SPF. UVA, there is no official rating. Now, this is kind of beyond our levels, but it's kind of, I thought it was interesting. You can have different kinds of ingredients, organic versus inorganic, and the organic, these are all supposed to be little atoms. The black is carbon, the white is hydrogen, and the red is oxygen. But nice little Tinker Toy set. So they will actually absorb incoming UV and put it out as heat, outgoing. Isn't that kind of cool? I guess your skin would get hotter, but that's amazing. It takes something that's so much higher in energy and is able to shift it to a harmless radiation energy. All right, so they yep. But this is the one that most people are familiar with, the inorganics. These don't absorb them, they deflect them. And they don't like the way it looks, so what did they do? They figured out how to make little, nano means 10 to the minus 9, so these are tiny, tiny little particles. Still zinc oxide, same stuff, smaller size particles, but notice what they do. They don't absorb the UV and convert it to heat energy like the organics. These guys just deflect it. It's like a little mirror right there. Okay. Titanium oxide's another one. And then the next thing we'll talk about is vibrating molecules. Remember, vibrating means that they're interacting with IR energy. Great.